If we had something like 0 over 0, then that was going to give us a point of discontinuity, or sometimes we just refer to it as a whole. Okay. Yeah, let's write that down. Need a common factor in f of x and g of x. Okay. All right, let's take this, let's shrink it down a little bit so I have some more room to write the other stuff. All right, what else do we see? If g of x is 0, okay, so if you have f of x over g of x and you get a 0 on the bottom, okay, and that just means that we have a number on the top, but the 0 is only on the bottom. Yeah, we don't have a hole in our graph, but we actually have a vertical asymptote there. Okay. And so for this one, maybe we can say that there's no common factor between f of x and g of x. Okay, so I think you saw a graph that maybe looked like a parabola, but then there was actually like a point missing from the parabola, right? So that would be an example of maybe at that place there was a common factor in the top and the bottom, and so that's how we ended up with the hole there. But I think there was also another graph earlier that they asked you to sketch, and you got something kind of like this. And that one has not a hole, but a vertical asymptote between our two branches, okay? Any other patterns that you noticed or questions that you have? Okay. Well, let's kind of take a break from this for a moment, okay? I think those are some really good patterns or summaries that you noticed from the exploration, okay? But let's take a look at what this whole section is really about. Okay. Some of the graphs had r. Was that just another variable? Do you mean like they said r of x? Is that what you mean by that? Yeah, so r of x is just like, you could name a function whatever you want. So it's just like f of x is just the name of a function, okay? It's not a specific function, it's just another letter to call it. All right, and Eric, you asked a question. There was r of x equals x squared plus 4 times something else over something else, right? And they wanted those question marks to be filled in by you, all right? So let's see what they're saying. They want the indeterminate. They say that it's indeterminate at x equals -1, okay? So if I have something at x equals -1, what's the factor that goes with that? So think back to 3.6 when we said like, hey, we have a 0 at x equals 2. The factor that goes with it is x minus 2. So how do we get from the 0 to the factor? Okay, yeah, we just moved the number to the same side as the x. And so what ISA says here is that you have, if there is a whole, okay, so indeterminate means that there's a whole at x equals -1, then x plus 1 is a factor of f of x and g of x. And so what we're going to put where those question marks are is we're going to put x plus 1 and x plus 1. Okay? So let's kind of take a look at how this connects to some of the patterns that folks saw. So one of the patterns that folks said was that if you have 0 over 0, you're going to get a point of discontinuity or a whole. And we said we need a common factor in f of x and g of x. And so that's exactly what we have here now with the x plus 1 and the x plus 1. The common factor on the top and the bottom means there's going to be a whole at x equals -1. So it'll look just like a parabola, except there's one point that's missing from the parabola. Okay, so when you plug that in, it looks like a parabola. One of the downsides about Desmos, it doesn't usually show you the whole so obviously. So what you might want to do is when you go to the graph, just like click on the graph at x equals -1, like wherever it is, and it should actually pop up and say -1, comma, undefined. Okay, so that's definitely one downside. You don't necessarily see the whole, okay, but when we draw them, we're going to be drawing the whole and making it a little bit more obvious, okay? No, that's fine, Eric. Okay, so Richard says the vertex of the parabola was 0, comma, -4. Yeah, so if they gave us this, we could also do -8 at the end to kind of shift it all down to meet, or you could have changed the plus to the minus and that would have been okay too, right? So there's more than one way to get to the same graph. Okay. Any other clarifying questions right now? And it's okay if you're feeling a little overwhelmed. I do want to summarize this at the end. I don't want to just be like, here, explore, and then learn, and then just get it. All right, I want to support you along this process. Okay, so maybe what we can do is take a look at, like, you know, from a more traditional lesson-y sort of situation, how we might approach the same ideas that you just explored earlier this morning, okay? So what we've been looking at in 3.7, and that includes the warm-up that we did this morning and the exploration that we did just now, okay? But a rational function is what we're really looking at. And a rational function actually comes from the ratio of two polynomial functions, okay? So we spent the whole chapter talking about polynomial functions just by themselves. But what we're looking at in this last section is what happens when we divide two polynomial functions, okay? So for example, we typically say f of x is a rational function if we have one polynomial on the top, all right? So let's say we have p of x, and that is just a name for a function. It doesn't really, the p doesn't really mean anything. It's just the letter we typically use for the numerator of a rational function, okay? And then on the bottom, we have another function, q of x, right? Now, p of x and q of x are both polynomial functions, and we're dividing them to get the rational function. Now, it's really important that we make note that q of x cannot be equal to 0, okay? Because when we divide by 0, that's when we start to have problems, especially if the whole function is 0. There might be points where q of x is 0, but we don't want the whole function to be 0, okay? So what we're going to focus on for this last part of class is we're going to focus on connecting the idea of the equation to the graph of the function, all right? And we're going to look at 3 specific things about rational functions that make them kind of special, all right? So the first thing that we're going to look at is this thing called end behavior, right? Now we've talked about end behavior before, but one of the things that is really important for us to know is that when we have rational functions, we can have horizontal asymptotes. Those typically happen in a rational function, okay? And so here's how we can find out whether our rational function has a horizontal asymptote or not. So here's what we're going to do. We're going to look at the degrees of the numerator and the denominator. So remember, we learned how to find the degrees. If it's in standard form, we just pick the highest one. But if it's in factored form, we have to add up all the degrees. Okay, we're still going to use that here. But if we compare the degrees of the top and the bottom, if the degree of the top is smaller than the degree of the bottom, okay, then what you're going to end up with is a horizontal asymptote at y equals 0. And that's going to happen every single time you have a function where the degree of the numerator is less than the degree of the denominator. A second case is that you might have the degree of the numerator is actually bigger than the degree of the denominator. So the top overpowers the bottom. In that case, there is no horizontal asymptote, and there's actually something called a slant asymptote. I'm not going to have us worry so much about the slant asymptote. I just want us to know that if the power on the top is bigger than the power on the bottom, then you're going to end up with no horizontal asymptote. And yes, Yithan, a slant asymptote is the same as an oblique asymptote, okay? So some of you might have heard that word before, that this is also called an oblique asymptote. All right, so there's one more situation when we compare the degrees of the top and the bottom. So when the degrees of the top and the bottom are equal, okay, then we have a horizontal asymptote at the ratio of the leading coefficients, meaning that we have to find the leading coefficients and we have to divide them. Okay, and when we do that, we'll get the equation for that horizontal asymptote. So I just want to squeeze in maybe like 2 or 3 quick examples here, all right? So let's say we had f of x equals 3x squared minus 2x plus 5 divided by 4 minus 6x squared plus 13x. Okay? So what is the degree on the top? Can someone tell me what the degree on the top is? Yeah, the degree on the top is 2. Excellent. All right, because we got that highest power there. It's in standard form, so we just picked the highest one. What about the degree on the bottom? Same. Okay, I actually really like the way you said that. They're the same. So how do we find our horizontal asymptote here? because there is one. How do we find our horizontal asymptote? Is it the pink case, the orange case, or the green case? It's the green case. Okay, so we're looking at where the horizontal asymptotes, the degrees are equal. So the horizontal asymptote is the ratio of the leading coefficient. So the leading coefficient on the top is, whoops, is the 3, because that's the coefficient of the leading term. Okay. And the coefficient on the bottom, the leading coefficient, is the one that goes with the one with the highest power. So it's -6. So we can say that there's a horizontal asymptote at y equals -3/6, or we would reduce that to -1/2. Okay? That's sort of an example of how we use this rule. Now, how could I change my f of x, the one that I had over there? How can I change that so that it has a horizontal asymptote at y equals 0? Okay, so how do I change my f of x so that I have a horizontal asymptote at y equals 0? Okay, I could change the degree of the top. That would give me a third degree on the top and a second degree on the bottom. All right, how would you like to modify your statement? If we want the pink case, we want the horizontal asymptote to be at y equals 0. Okay, cool. These are both good ways that we could approach it. So one way is someone said, well, you keep the top the same and you make the power on the bottom bigger. So we could do an x cubed on the bottom. Now the power on the bottom is bigger, and that's going to give us a horizontal asymptote at y equals 0. Okay. And the other option, okay, and there's a lot of options, is that we could get rid of the 3x squared on the top. So keep everything else, but just get rid of that highest power. And now when we compare the powers, I've got a power of 1 on the top and a power of 2 on the bottom. And those are both ways in which we could nicely suggest that this graph have a horizontal asymptote at y equals 0. Okay. Now, if we did what was initially suggested, which is change the power on the top to a 3, that would give us the orange case because the power on the top is larger than the power on the bottom. Okay. Yeah, we're not saying, oh, everything about the graph, everything else about the graph is the same. We're just saying, like, what do we need to do in order to get a graph that has these characteristics? So if I say write a function where there's a horizontal asymptote at y equals 0, you could write either one of these options here. Or you could write any option as long as the degree on the bottom is bigger than the degree on the top. Right? So we're looking at this more conceptually, like what's the idea behind it, rather than computing things right now. Right, right, right. it was more like, here's an equation that I just made up, and let's see what this equation does. Does it have a horizontal asymptote or not? Okay, well, it does. It has one at x equal or y equals -1/2. And now, how do we play with the idea of the powers so that we can get some of those other cases? Okay. So this was an example of different graphs for us to just kind of know, like, what are the degrees? How do we find them? Okay, so a reminder on how we find our degrees. And then thinking about, okay, how do we apply these rules about how we get horizontal asymptote? Yeah, so this section is definitely a little bit more, it's a different flavor than a lot of the other ones we've done because we're not necessarily computing things, but we're thinking about what patterns are true for given equations. Okay. All right. So now let's take a look at two other characteristics that are pretty special about rational functions. Okay. And we kind of talked about this above. But basically, if you have a situation where you end up with a number on the top and 0 on the bottom, okay, that is going to cause a vertical asymptote, right, where g of x equals 0. So wherever the denominator equals 0, that's going to give us a vertical asymptote. But one thing that we should check is there a 0 on the top at the same spot too? So if both f of x and g of x, meaning the top and the bottom of your rational function, equals 0, then there is a hole instead of a vertical asymptote. Okay? So you never have a vertical asymptote and a hole at the same time at the same place. You either have a vertical asymptote or you have a hole. Okay? You either have a vertical asymptote at that point or you have a hole. So let's take a look at just a couple quick examples. All right. Now, for these examples, we're going to look at the equations and say, like, is there a vertical asymptote? And if so, where is it? And is there a hole? And if there is a hole, where is that hole? Okay. So let's make up another function. Okay. So we're just making up a function. And let's say we have this x plus 1. Okay. So does this function have a vertical asymptote? Let's start there. Does this function have a vertical asymptote? Yes. So we have one vote for a yes. Can you tell us where there is a vertical asymptote? Like, or how do you know from the equation that there is? Okay. So this right here, that factor is only on the bottom, okay? The factor is only on the bottom. So this one means there is a vertical asymptote at x minus 2 equals 0. Or we want to solve that, we'll say there's a vertical asymptote at x equals 2. Okay. So there's only the bottom could be 0. That is our vertical asymptote. So this is our number divided by 0. Okay. But tell me what's happening with this x plus 1 factor. How is that one different? There's an x plus 1 on the top and an x plus 1 on the bottom. So we wouldn't say, oh, there's a vertical asymptote there. What's happening there? Yeah, exactly. These blue factors that are the same on the top and bottom mean that there's a hole at plus 1 equals 0 or x equals negative 1. Okay? So when the factor is only on the bottom, it causes a vertical asymptote. When the factor is the same on the top and the bottom, that causes a hole. Okay? So if you see a factor on the top and the bottom, that's going to be a hole. But if you see a factor that's only on the bottom, that's going to be a vertical asymptote. So let's make up a different function. We'll call it h of x. Okay. So let's say we have this function right here. Actually, let's get rid of that x on the end. Are there any holes or are there any vertical asymptotes, and how do you know? Okay, so how did you folks get that there's a hole at x equals negative 2? Okay, you factored the numerator. All right, so if we factor the numerator, we're going to get x plus 2 times x minus 2, right? And then on the bottom, we have x plus 2 times x minus 3. Okay, and so let's do our color coding here. Well, I can tell that there's a factor on the top that is the same as the factor on the bottom. So we can say that there is a hole at x plus 2 equals 0 or at x equals negative 2, right? That means if you threw this graph on Desmos and you clicked on x equals negative 2, it would be like negative 2 comma undefined. Okay, good. And then there's a vertical asymptote at x equals 3. Good. Yeah. So the only factor that's left on the bottom is this minus 3. Okay. And so that means there's a vertical asymptote at x minus 3 equals 0, or we can say x equals 3. Right. Yeah, so Ethan, you can definitely plug in numbers just to kind of see, but for some of the longer equations, it could definitely not work out that way for you. Okay. All right. So before we move on to the examples, tell me about the horizontal asymptote for f of x. Is there one? And if so, what is it? Okay, so Thea says that there's a horizontal asymptote at y equals 0 because the degree on the top is smaller than the degree on the bottom. Yeah, I agree with that. Good reasoning. Okay. Now, what do we say about h of x? Is there a horizontal asymptote or not? And if so, what is it? Okay, so if we compare these degrees here, we see that there's a degree of 2 on the top, but what's the degree on the bottom? All right, because I have a degree of 1 times 1. Those two will give me an x squared on the bottom. So yeah, the degrees are the same. And our leading coefficients, when we divide them, are just going to be 1. Okay? All right, so it looks like Val just posted something in the chat. Hi, Val.
Hey guys, just wanted to pop in and check in on you and remind you that my sessions are from 1 to 3 today and 3 to 5 on Wednesday. I haven't seen a lot of you, but I've also met so many of you. So if you can come to my sessions, that would be cool. If you have schedule conflicts, please pop into the tutoring center. I'm also there from 4 to 7 today and from 4 to 7 on Wednesday. So if you can't pop in at the normal time, pop in 4 to 7 Mondays and Wednesdays, and I'll be there. And come meet me and introduce yourself, whether you have questions or not.
Thank you. All right, so folks, are we ready to maybe jump into an example and kind of see how to tie this all together? Today's been a very long delayed gratification days. Yeah, for sure. Let me just scroll back up before we go down. This one right here. Alrighty, so let's take a look at this example right here, okay? I think we're only gonna get through examples 1 and 2, which is totally fine, okay? And we'll just take a look at the quiz and see what we need to modify from there. But in this case, we're going to start with our equation, and then we're going to find a bunch of different information about this equation, okay? So we have f of x equals x squared minus x minus 6 on the top. And then on the bottom, we have x minus 2 and x plus 1 squared. So before we do anything, what I'd like you to do is 2 things. First, I'd like you to keep the bottom the same, but I'd like you to factor the top. Okay. The second thing I'd like you to do is I'd like you to go to Desmos, type this equation in, and then sketch the graph that you see on the grid that I provided. Okay, so 2 things. 1, you're going to factor that numerator, and 2, you're going to go to Desmos, get a graph, and then sketch that graph down here. I'll give you a couple minutes to do that. And I'll graph on Desmos as well, so we can have something to look at together. All right. So anybody happen to have that numerator factored? X squared minus x minus 6. What does that factor into? All right, I've got an x plus 2 and an x minus 3. Okay, let's write that down and then maybe FOIL it back out in our heads just to make sure that we get what we had. So if I multiply x times x, I'll get x squared. That's good. Okay, my outer terms give me negative 3x. My inner terms give me 2x. So negative 3 plus 2 is negative 1. And then 2 times negative 3 gives me negative 6. Okay, good. All right. So this is one of the first things that you want to do when you get a rational function. If it's not factored for you, you want to go ahead and factor it, okay? And so once we have it factored, can someone tell me, do we have any holes in this particular rational function? And if we do, where is it? And if we don't, why not? All right, I've got one person saying there are no holes. Anybody else? Is there a hole or is there not a hole? No hole. Okay, good. And our reason for that is when we compare the factors on the top and the bottom, there are no common factors. Like x plus 2 is almost like x minus 2, but they're not the same, okay? And the top has an x minus 3 and the bottom has an x plus 1. So none of the factors are the same. We can go all the way down to where it says discontinuities from 0 over 0 and say there are no holes. Okay? So there's no holes, meaning that we don't need to draw them out. We can connect our different pieces of the function to each other. Okay? But while we're looking for holes, let's also look for discontinuities of the other type, which are vertical asymptotes. So looking at this, do we think there are any vertical asymptotes? And if we do, where are they? And if we don't, why not? Okay. X equals 1, or sorry, x equals negative 1 and x equals 2. Okay, because when we look at these, and I already forgot what color I used, but x minus 2 is a factor that's only in the denominator, and x plus 1 is a factor that's only in the denominator. And so you folks are exactly right. If we take those two, x minus 2 equals 0, and we solve, we'll get one vertical asymptote. And if we take the other factor and we set it equal to 0, and we solve, we'll get the other vertical asymptote. So there are two vertical asymptotes in this function. Now I asked you to throw this graph on Desmos, but we're going to kind of construct it here together. So I'm going to go ahead and draw in a vertical asymptote at x equals -1. And I'm going to draw one in at x equals 2. So this is x equals -1. This is x equals 2. Okay? All right, let's do one more thing here. Tell me about the end behavior. What is the end behavior of this particular function? And when I say end behavior, that's another way of saying, does it have a horizontal asymptote at y equals 0? Does it have a horizontal asymptote at y equals a number? Or does it have that slant or oblique asymptote? Okay. So let's go back to the equation so you can see it. What are we thinking about end behavior? So what do we think? Is there a horizontal asymptote here? Like, what are the degrees on the top and bottom? Maybe we should start there. What's the degree on the top? Okay, the degree on the top is 2. Good. Okay, what about the degree on the bottom? I see a 2, I see a 3, I see another 3. Okay, I see a fixed 3. Okay. So the degree on the top is 2. And I think that one is pretty self-explanatory. Let me zoom in for a moment. This squared, it's in standard form. So we just take the highest one, the highest degree. But when we look at the bottom, we kind of have to add because it's in factored form. So we're really adding a 1 and a 2 to get us the third degree on the bottom. Okay. So if we go down to where we're talking about end behavior, let's actually use the explanation to help us make our decision. So we can say that the degree of the numerator equals 2, and the degree of the denominator equals 3, right? So which one's smaller? Is the top smaller than the bottom, or is the bottom smaller than the top, or are they equal? I mean, I tell they're not equal to each other. We could say that the degree of the numerator is smaller than the degree of the denominator. So because the degree of the numerator is smaller than the degree of the denominator, what conclusion can we draw from that? Yeah, that we have a horizontal asymptote at y equals 0. Okay. And again, that just goes back to those rules we saw on the previous page, right? So if I scroll up here for a moment, we're looking at the pink case where the degree of the numerator is less than the degree of the denominator, okay? And when that happens, there's a horizontal asymptote at y equals 0. Okay? Now, if it was the other way around, there was like a higher power on the top than the bottom, then you would say that there's an oblique asymptote or there's no horizontal asymptote. Okay. So I'm going to go ahead and, sorry, that was a lot of moving on the screen. I'm going to go ahead and draw in the horizontal asymptote. We know now that we have one at y equals 0. So if you graphed your function on Desmos, do you see a vertical asymptote at -1 and 2? And does it sort of flatten out at y equals 0 at the ends? You should be able to see that on the graph. Okay. All right. So let's go ahead and find our X and Y-intercepts. And that's a good review for tomorrow's exam anyway, because when we're finding X and Y-intercept, we do the same method no matter how fancy or not fancy the function is, all right? So let's start with the Y-intercept because I think that one was a little bit easier. How do we find a Y-intercept? When we were looking at polynomials, how did we find a Y-intercept? Yeah, we just plug in x equals 0. I love that. I love that. So let's do that. F of 0 equals, I'm going to use the factored form, but it doesn't actually matter which one you use, right? 0 plus 2, 0 minus 3, 0 minus 2, 0 plus 1 squared. Okay, and let's calculate that out. What do we get in the numerator here? All right, yeah, I agree. We get a -6. 2 times the -3 gives us -6. And what do we get in the denominator here? -2, good. Okay, and we would simplify that to be 3. And so we know that this rational function has a y-intercept of 0, 3. Okay, so I'm going to go ahead and plot that point. 0, 0, positive 3. So I'm going to go ahead and plot that point right there. That's my y-intercept. Okay. All right. Now, how do we find the x-intercept? Exactly. We don't put in 0 for x, we put 0 in for y, okay? So we want to say f of x equals 0, which for us means that this big long equation equals 0, okay? Now, I don't know about you, but when I look at an equation like this, I'm like, wow, that's kind of a really long, complicated equation. Like, how am I supposed to find out how it equals 0? Like, that seems really hard. So let's kind of take a step back for a moment from that complicated equation. And I'm wondering if you can answer a few of these questions for me. What's 0 divided by 2? Good. It's 0. Okay. What about 0 divided by pi? Yeah, 0. Okay. What about 0 divided by negative 11? Zero. Okay. What about 1 divided by 100? .01. Okay. So tell me this. If I have a fraction and I want that fraction to give me 0 as an answer, what needs to be true about that fraction? Yeah, we want to say if we want 0 to come out of a fraction, okay? We want that answer to be 0. Like we wanted this to be 0. Well, our numerator had to be 0. If we wanted this to be 0, our numerator had to be 0. If we wanted this to be 0, our numerator had to be 0. And when we divided anything else on the top, even if it was a small number, we didn't get 0. So the only way you can get 0 out of a fraction is you have to have 0 in the top. Okay. So what that means is when we're trying to find our x-intercepts for rational functions, even though this is a long, complicated equation, because it's a fraction, we only need to say, when does the top equal 0? Because that is the only way we're going to get 0 out. It doesn't even matter what happens on the bottom. We just need to have the numerator equal to 0. Correct, correct. And so this is definitely assuming there's not a hole there, okay? Otherwise it would be undefined. But once we've gotten rid of our common factors, the only thing we need to do to find the x-intercepts is set the top equal to 0. And so this is going to give us x equals -2 as an x-intercept, which we can say is -2, 0, and x equals 3 or 3, 0 as our other x-intercept. And so if we plot those on our graph, we'll have an x-intercept here, and we'll have an x-intercept here. And if you look at the graph that Desmos created, you should see those two x-intercepts as well as that y-intercept, okay? All right. So what we have so far is the important characteristics for our graph. Now the rest of it, I'm not going to make us figure out how it happens by hand, but you can definitely do that, okay? You can definitely do that. But for right now, let's just go ahead and fill in the rest of the graph based on what we see on Desmos, okay? And so we see that there's sort of like this U shape in the middle, like this, right? And then it looks like on the right-hand side, it kind of does like this, comes from the bottom, crosses through, and then flattens out. And it looks like on the left-hand side, it starts at the top, it goes down, and then flattens out towards that end. Okay. Yes. All right. So among lies that you've been told in the past, all right? That applies right now. Lies you've been told that you can never cross an asymptote. That is a lie, okay? You can cross an asymptote, but you have to be specific. You cannot cross a vertical asymptote. However, you can cross a horizontal asymptote. All right, and here's a little bit, a picture to help us think about why that is. I didn't say that it doesn't cross it. If you have a vertical asymptote and you cross that vertical asymptote, this fails the vertical line test, which would mean that it's not a function. So that is why you cannot cross a vertical asymptote. However, we're going to take a look at some functions in calculus, where maybe it kind of looks like, maybe it kind of looks like this. Okay. This has a horizontal asymptote, but it crosses it a whole bunch of times. It's okay to cross a horizontal asymptote because it doesn't then fail the vertical line test. Okay? Yes, you cannot cross a vertical asymptote, but you can cross a horizontal asymptote. Sine and cosine, we're going to get to that next course. This one, if you wanted to look ahead, this function is sine x over x. You can kind of play around with that one, but we'll definitely see that again when we get to calculus. All right, here's one last thing we're going to fill in, which is expressing the domain, okay? So the domain is all of the x values that the function can be, all right? It's all of the x values that the function can be. So one of the easiest ways to come up with a domain for something like this is to say, where can x not be? And according to our discontinuities, okay, so our discontinuities, they tell us about our domain. So our domain can be everything except x equals 2, I don't know what you just said, and x equals -1, okay? Those are only exceptions. So when we write these out, we're going to start from -infinity. What's the next value that it gets to when we come from -infinity? Does it get to -1 first, or does it get to 2 first? It gets to -1. So that's the next one I'm going to write here. Now, can x equal -1 according to this function? Yeah, there's not a value there, so we have to seal it with a parenthesis, okay? Then we keep that fancy u, which means that you're saying there's another part to it. And then we go from -1 to 2, we close it, and we go from 2 to infinity. And these two, the -1s, come from the fact that there's a vertical asymptote at x equals -1. And these 2's come from a vertical asymptote at x equals 2. All right, so I'm going to zoom in a little bit so we can so we can see the whole big problem on one page. All right. Now, I know earlier when we checked in at 9:30 this morning, everyone was kind of like, "Oh, I'm really tired." But how are we feeling right now? How are the brains feeling? Still tired. Okay. And how are we feeling about the content? Okay, better than when we were doing the Desmos exercises, feeling okay about it, feeling better about it. Now, I think it's really important here that if you're not feeling great about it, you also share that too, because otherwise, I think everybody's feeling super good about this. And you can private message me that. You don't have to throw it on the public chat. That's totally fine. Okay. Antonio, what's your question about the domain interval notation? It is. So that -1, 2, that's not a point, okay? That -1, 2, what it does is it talks about this part of the graph. See how it's between an x value of -1 and +2? That's what that -1 to +2 means. It means that part of the graph. So if you don't include it, then it's like you're missing a whole part to your graph. Does that make sense? Okay. What is the yellow line I highlighted? The yellow line is the horizontal asymptote at y equals 0. Okay. Ethan, that's definitely a longer question. I can send you like a little thing about it, like how you know which way it's going. Okay. And that's actually something we're going to explore a little bit more in calculus. Like, how do we know which direction it's going? Okay, cool. All right. So, here's what I will have us do right now. Okay. So no, we're not going to need to graph on the exam, but I might ask you to like draw the asymptotes in and like label um label the like X intercepts and the Y intercepts. So like before we connected out all the things that we drew, those would be okay to ask you to sketch. But I don't expect you to know how like the whole graph looks, if that makes sense. Okay. So again, we're looking at graphing like the vertical asymptotes, the horizontal asymptotes, and like the X and Y intercepts, knowing how to find those, but not necessarily how to connect everything. Okay. All right. So I think what we're gonna do here is actually stop going to stop sharing this. Okay, so